Hello, welcome to Jedi Lesson 8. This is week 5 homework, problem 1. So the team moderating a space probe exploring the outer solar system finds that the radio transmissions from the probe take 2.9 hours to reach Earth. How distant in meters is the probe? Alright, so first I want to start off by writing down an equation that might be of use for us since we're going to use the speed of light constant. So we have d equals c times time. And then I want to go ahead and define some variables. So the first is d, which is our distance. And it's measured by meters. And then we have our constant, oh yes, and the value given here is 3.13 times 10 to the 12th meters. And then we have c equals our speed of light. So I can go ahead and write speed of light here. And the SI units for this is in meters per second. And then lastly we have, that is 3.00 times 10 to the 8 meters per second. That's our constant. And then lastly we have time, which is represented by t. And the SI units for time are going to be seconds. And then we got to find that time, which is what we're asked here in the problem. Yeah, wait, I messed up. I accidentally gave the answer too far in advance. So yeah, we're going to find that together in terms of distance. But alright, so I think in order to start with this problem, it'd be really helpful to draw a picture just so that we can wrap our mind around what we're going to tackle in this problem. So the team monitoring space probe exploring the outer solar system finds the radio transmissions from the probe that take 2.9 hours to reach Earth. So I'm going to go ahead and draw Earth first. Alright, gonna add some water, make it a little fancy. And then that's our Earth, so then we want to find, we also have our probe, which is what sends that radio transmission. So this can be our probe. And then we have our radio transmission that is sent. It takes 2.9 hours to send, or to reach Earth. And then we're trying to find that distance, so we don't know what that is yet. And that's okay, we're going to try to figure that out. And that's going to be in meters. Alright, so now that we have this, we can go ahead and start solving the problem. So one thing that we can do first is go ahead and substitute everything. So we have that 2.9 hours. Right, we have to turn it into seconds first. So we have times 3,600 seconds over 1 hour. And then our hours cancel out. And then we plug that into a calculator, we get 10,440 seconds. And then now we can go ahead and plug that into our distance equation. So we have the constant is 3.00 times 10 to the 8th meters per second. And then multiply that by our time, 10,440 seconds that we got previously. And then once we plug that into our calculator, we get 3.13 times 10 to the 12th meters. And that's in meters because those seconds cancel out. And then we can go ahead and see if that matches, or plug that in, to Wiley. And yeah, that checks out. Alright, so yeah, now we solved that problem. Alright, so now we can move on to our next problem. Oh, my pen isn't working. Alright, Neil A. Armstrong was the first person to walk on the moon. The distance between the Earth and the moon is 3.5 times 10 to the 8th meters. Find the time it took for his voice to reach the Earth via radio waves. And then B. Someday a person will walk on Mars, which is 5.60 times 10 meters from the Earth at the point of the closest approach. Determine the minimum time that it will be required for a message from Mars to reach the Earth via radio waves. Alright, so again, I want to start off by drawing an image that works for us. And we're going to start by drawing our Earth first. Okay. Trying to make it fancy like the last one. That's some water. And then we have distance between the Earth and the moon. Okay, so we're going to draw our moon next. And we know that distance, so that's important to write down in this picture, just for it to make it easier for us. Okay. And then that's going to be d equals 3.85 times 10 to the 8th meters. Perfect. Find the time it took for this voice to reach Earth via radio waves. Okay, so then we want to draw some radio waves These could be the little radio waves because they're that, and that's the time we don't know. I'm just going to leave this for the first problem, then we can draw the rest of the image I have in mind for the second part. So first, we know the equation we're going to use is our t, our time, equals our distance over the speed of light. And I think it's important to go ahead and define some. So we know t is time. SI units for t are going to be our seconds. And then we have d is distance, which is going to be measured by meters. And then v, which I guess we could just use c because it's like the speed of light constant. That is, 1 second. Okay, so that's going to be, our SI units for that is going to be our meters per second. All right, and then that's also a constant, so that's 3.00 times 10 to the 8th meters per second, and we're going to use this value in our equation again, just like the previous problem that we learned from. All right, so now we can go ahead and plug all those values in. We have our time equals, oh yeah, the distance is going to be the 3.85, which we already wrote down there. Okay, but the time equals our distance, the 3.85 times 10 to the 8th meters. And then we have our c, which is going to be a constant, 3.00 times 10 to the 8 meters per second. And then once we plug that into the calculator, meters cancel out, and we're left with our 1.285 seconds. Sorry, 1.28 seconds. Okay, and then that's the first part. The second part says, someday a person will walk on Mars, which is 5.60 times 10 to the 10th meters from the Earth at the point of the closest approach. Determine the minimum time that will take required for a message from Mars to reach the Earth via radio waves. Okay, so we could draw Mars first. My pen is having some technical difficulties. Sorry about that. 1 second. Okay, so we have Mars. And then required to reach Earth. Yeah, let me move this distance because it kind of gets in the way. It makes me think that we're going to use this distance once more, but we have a new distance, so. Oh my goodness. That's getting stuck. Okay. Just going to shrink it and put it there. All right, that's better. Just so I don't get confused with our values. So now that we have Mars, our new distance is going to be from Earth to Mars. And I could do it in brown so we have a distinction. That's our 5.60 times 10 to the 10th meters. And then we can go ahead and maybe I'll do it in orange. Just so that we know that the time we're looking for is different, for the radio waves to get there from the Mars to Earth. It's our new time that we're looking for. Perfect. So similar approach that we used for part A, we're going to go ahead and take that knowledge to part B. So first we're going to start with our equation again. Okay. Yeah. Okay, so gonna do the distance, and then our constant is 3.00 times 10 to the 8th meters per second. And then we can go ahead and plug that into our equation. T equals our distance, which is our new one, over the constant. And then plugging into that calculator, that should give us something like 1.867, I rounded it up, times 10 to the 2 seconds. Our meters cancel out, so we're left with seconds. But for some reason, when I plugged it into Wiley Plus, it didn't take it. So I went ahead and just moved the decimal, and I ended up with 186, I believe. So I plugged it in as 186.67 seconds. And then we can go ahead and check that. Beautiful. Both answers match up. So again, we have our time, 1.28 seconds. Then our second time is 108.